Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, our mission is to transform some of that destructive hate energy into constructive love energy. Mathematics is part of all that surrounds us. Just pause and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over. Now let's get down to some serious math. This is part of our continuing series on algebra, and this is video number 4, and it's essentially a continuation from video 3. And let's have a look at question C here. We clearly have a quotient or a rational function here. The numerator is linear because m appears to the power 1. The denominator is quadratic. The degree is 2. And the objective is to simplify this expression by factoring. And the idea here is to factor the denominator. Of course, the numerator is already linear, so there's nothing to factor. There's no GCF. We have to factor the trinomial in the denominator, and that trinomial easily factors as m plus 3 dot m plus 7. When you expand the denominator here, the factored form, it's easily verified that you get the original m squared plus 10m plus 21. At this stage, you notice that these two linear factors cancel, so m plus 3 cancels out with m plus 3. And the final result is 1 all over m plus 7. And as indicated previously, this appears to be the end of the problem. In other words, the original rational expression simplifies to 1 all over m plus 7. However, it's not quite done. You must impose restrictions. Okay. There are a couple of math crimes, if you will, that you can commit. One is less severe than the other. One math crime is the 0 over 0 crime, and it essentially corresponds to a hole in the graph if we were trying to graph the original function. The second crime, that is to say mathematical crime, is a 1 over 0 crime, and this corresponds to a vertical asymptote if we were to graph the original rational function. Okay, this crime over here, the whole crime, is not too substantial, and the 1 over 0 crime, which corresponds to a vertical asymptote, is very severe, and you could get the death penalty for committing that kind of crime. So we want to avoid going to jail. We want to avoid the death penalty, so we have to impose restrictions. The cancellation up here will give us a 0 over 0 type restriction. We know that m plus 3 cannot be equal to 0, otherwise we'd be violating the 0 over 0 restriction. Okay, so you cannot have 0 over 0, otherwise jail time. You cannot have 1 over 0, otherwise death penalty. So we have m plus 3 not equal to 0, solve for m cannot be equal to negative 3. So as long as m is not equal to negative 3, then the original corresponds to the final. Also, at the end, we look at the denominator. The denominator is m plus 7. We want to make sure that denominator is never equal to 0, so we set m plus 7 not equal to 0. Solve for m, you get m is not equal to negative 7. So provided the variable is not equal to negative 3, which corresponds to a hole, and m is not equal to negative 7, which corresponds to a vertical asymptote, aka VA, then the original function may be written as the final function that we have down here, provided you put these restrictions down. So to recap, the original function is identical to the final one, or the reduced form, provided we impose these restrictions. So let's go on to another question. Part D is a similar question. We have a quotient or a rational function. The numerator over here is quadratic, the denominator is quadratic, and the idea is to factor both numerator and denominator. So when we factor the numerator, and again we'll go through rigorous factoring procedures or techniques in future videos, so don't worry about the factoring right now, okay, the details of the factoring. The numerator factors as 2x minus 3, 2x plus 1. When you re-expand that, you can verify that you get the numerator. And the denominator is just a difference of squares, which factors as 2x minus 3, 2x plus 3. And now look for cancellations. And if we look for cancellations, 2x minus 3 cancels out with 2x minus 3. And we get a 2x plus 1 all over 2x plus 3 as the reduced form. And beware of the cancellation. Now we have to impose the restrictions. The 0 over 0 restriction comes from the cancellation. So we have to impose that 2x minus 3 is not equal to 0. If you solve this for x, you get x is not equal to 3 over 2. At the end, we have to impose the 1 over 0 restriction. So at the end, we look at the denominator, 2x plus 3, and we have to ensure that it's not equal to 0. If you solve for x, you get x is not equal to minus 3 over 2. So this is a whole restriction. That's a VA restriction. Okay, so let's go on to the next slide. We have the same sort of question here. We have a quadratic numerator in two variables. We have a quadratic denominator in two variables. And there are no GCFs to factor out, so you acknowledge that. There are no greatest common factors. And the idea is to factor both numerator and denominator. Again, we won't go through the factoring details. That will be done subsequently in another video. But the numerator easily factors as x minus y, bracket 3x plus y. And the denominator easily factors as 3x plus y dot x plus y. You look for cancellations, and indeed 3x plus y cancels out with 3x plus y. So the reduced form is x minus y over x plus y. And always take note of the cancellation. And then, of course, at the end, we need to restrict. The 0 over 0 restriction comes from the cancellation. And the cancellation is 3x plus y. So we have to ensure that 3x plus y is not equal to 0. At the end, there's no need to solve this for either x or y because it's a two-variable restriction. It's fine to leave it as a linear combination of x and y. There's really no need to solve for y. I mean, you could if you wanted to, but you don't have to. Over here, turning to the 1 over 0 restriction, we look at the end of the problem and look at the denominator, x plus y, and we want to ensure that x plus y is not equal to 0. Otherwise, you'd get like a 1 over 0 form. Okay, so if we look carefully at these restrictions, okay, try to stay with me on this. The original function over here is a two-variable function. We can actually graph this, and it really corresponds to a surface over the xy plane. Okay, so it's like a 3D problem over the xy plane. I'm not going to do it for you here. Perhaps at some other point in time I'll do it for you. But it corresponds to a surface that exists over the xy plane. And this over here, if you solve for y, you get y equals minus 3x. That means along y equals 3x, which is along a line in the xy plane, the surface will have holes everywhere along that line. Okay, so the surface in 3D will have a hole everywhere along that line. And over here, if we solve for y, we get y is equal to minus x. That's another line in the xy plane. So the surface will have a vertical plane as an asymptote in the xy plane. I know you can't visualize this right now, so if you can't, don't worry about it. Maybe in a future video, I'll show you the restrictions over here in 3D format. Okay, let's turn to the next slide. Question 12 says simplifying rational expressions. aka fractional with restrictions, and these will be like multiplication division problems. Okay, there are two distinct types of problems, and one of them is multiplication and division, and the other one would be addition subtraction, which I call LCD problems. COEFF is short form for coefficient. It's the number attached to a variable. Okay, so let's look at Q12A. We have 6x over 8y times 2y squared over 3x. To simplify this expression, this is a single cluster, by the way. There are no plus or minuses. The idea is to move all the coefficients over to the left. When you do that, you move the 6 over 8 over here and the 2/3 over here. But I automatically joined the 6 and the 2 because they're both in the numerator. And I joined the 8 and the 3 because they're both in the denominator. And then you'll notice you see two variables, x and y. And we can certainly use exponent laws to our advantage over here to simplify simplify further. Okay, so the base, if we turn our attention to base x, we pick up a 1 on top and then minus 1. So we get x to the power 1 minus 1. For the y, we pick up a 2 on top and then a 1 becomes minus 1 on the bottom. So we get y to the power 2 minus 1. Okay, remember, this is all about exponent laws. So if you're a little bit weak here, go back to my playlist on exponent laws and go through some of those questions there, and you'll refamiliarize yourself with performing operations like this. Okay, then we simplify. It's easy to see that 12 over 24 is just 1 over 2. And then we have x to the power 0. And then we have y to the power 1. At the end, x to the power 0 is 1. So we have 1/2 dot y, which is the same as y over 2. That's the end of the problem. Okay, now, do you remember I said that when you look at the operations in the exponents here, whenever you have a minus sign, like minus 1, what you're really doing is doing a cancellation. When you have a minus 1 over here, you're really doing a cancellation. So there are cancellation restrictions on both x and y. Okay, so if we go to the cancellation restrictions over here, which corresponds to 0 over 0, we notice that x cannot be equal to 0 and y cannot be equal to 0. At the end over here, the only denominator is 2, so it certainly can't be equal to 0, so there are no 1 over 0 restrictions. There are only 0 over 0 restrictions, no 1 over 0 restrictions. Okay, so we'll go on to the next slide. Same sort of problem over here for part C. You see a big cluster. It's a single cluster, but it's only one cluster. And the coefficients are 2, 6, 5, and 10. But the big difference over here is that this is division. And you know how to take care of division. Dividing by a over b is the same as multiplying by b over a. Okay, so this is called invert and multiply. Or you can think of it as keep dot flip. I talk about keep dot flip in one of the videos in the exponents section. Okay, so that's what you do. You keep this guy and you flip that guy. That's the very first thing you do. So this is just a drop down. The division becomes multiplication and you flip the fraction. So don't do anything until you do the invert and multiply or the keep dot flip. Okay, so keep the first fraction. That division sign becomes multiplication, and then you flip the second fraction. At this point, move all the coefficients over to the left. So 2 moves over to the left, 10 moves over, 5 moves over, and 6 moves over. And we get a 2.10 over 5.6. And then we take care of all the variable bases. We have base A, base B, base C. So over here we get a to the power 1 minus 1. There it is right there. And then we get b to the power 1 plus 1 minus 1. And there it is right there. And then we get c to the power negative 1 minus 1. In other words, c to the power 0 minus 2. Okay, which is the same thing. Okay, and notice the negative sign there, and the negative sign there, and the negative sign there. That means we've done some cancellations. Okay. So anyway, we can simplify 20 over 30 is 2/3. Then we get a to the power 0, b to the power 1, c to the power -2. A to the power 0 is just 1, b to the power 1 is just b, and c to the -2 gets downshifted. So at the end of the day, we have 2b all over 3c squared. So this is the reduced form of that original form. And of course, that is the end of the problem, except for the restrictions that we need to impose. Okay, recall what I told you. Whenever using exponent laws, if you ever see a negative in the exponent, like -1, -1, -2, that indicates cancellation restrictions. So that means that a cannot be equal to 0, b cannot be equal to 0, and c cannot be equal to 0. At the end, you examine the denominator, and the denominator only. 3 is certainly not equal to 0, but c squared could be equal to 0. And the only time that c squared is equal to 0 is if c is equal to 0. So you have to ensure that c is not equal to 0. So initially we thought that we had a whole restriction on c, but finally that whole restriction has transformed to a vertical asymptote restriction. So initially we thought that c was just going to go to jail if the crime was committed here. But then we found out that the C was actually going to get the death penalty because it would wind up committing this kind of crime. Okay, so initially we thought it was a 0/0 crime, and now it becomes a 1/0 crime if it's committed. But of course we impose restrictions to ensure that nobody goes to jail and nobody dies. Okay, we don't want anybody going to jail, we don't want anybody to die, and that's why we need the restrictions. Okay, let's go on to the next slide. Same sort of idea as the ones we just finished doing. This is question 13a. It's just a little bit more complicated, but the same sort of idea. If you look at this whole expression over here, this will constitute one big cluster. I see a multiplication sign here and a division sign there. The first thing to do is to copy paste these two terms, do nothing, convert that division to multiplication, and flip the fraction. Okay? So all you do is drop these two down because they're already being multiplied. Division means flip the second fraction, and that's what I did. When you flip the second fraction, you get x dot y squared, and then what I did over here is just expanded this using exponent laws. So 3 squared is 9, and then you get x squared. So you get 9x squared altogether. Now you have all multiplications, and what you have to do is left extract. That's what I call it, left extracting all the coefficients. On top, the only coefficient is 1, so you put a 1 down. On the bottom, you get a 2.2.9, so you put it down. Next, we deal with the x's. Okay, again, this comes down to exponent laws. When we deal with the x's, we pick up a 2 here, 1 there, 1 there. So we get 2 plus 1 plus 1, and then minus 1, minus 2, because they're on the bottom. If we consider base y now, we get a 2 on top. So there's the 2 right there. And 1 on the bottom becomes minus 1, and 2 on the bottom becomes minus 2. Okay, so you might want to review your laws of exponents in the exponents playlist that I have on the YouTube site. Let's continue over here. If we simplify the coefficient over here, we get 1 over 36, no problem. And then if we simplify this little integer string over here, we get x to the power 1. And if we simplify this integer string, we get y to the power -1. X to the power 1, of course, is x. 36 goes on the bottom, and this gets downshifted to the bottom. At the end, we get x all over 36.y, and that will constitute the end of the problem. That's the reduced form of that original mess. However, we have to impose restrictions so nobody goes to jail and nobody dies. Okay, so if we look at this this line right here, we see all these negative exponents. That indicates cancellation restrictions, the negative exponents. And so we must ensure that x is not equal to 0, and then y is not equal to 0. At the end, 36 is certainly not equal to 0, but y could be equal to 0. So we have to ensure that y is not equal to 0. Because if y was equal to 0, you'd get a 1 over 0 restriction, or 1 over 0 violation, if you will. So over here, notice the y not equal to 0 appears on the left as a cancellation restriction or a hole. It also appears on the right as a vertical asymptote restriction. So the vertical asymptote restriction always overrides the hole. We originally thought it was a hole, but it turned out to be a vertical asymptote. Okay? So when two restrictions, identical restrictions, appear both on the left and the right, the one on the right is the one that applies. It overrides the one on the left. A hole is much less severe than a vertical asymptote. So you get death penalty for vertical asymptote, and you get jail time for having a hole. Okay, they're going to nail you for this. They won't even bother with the hole. Okay, so if you stole a chocolate bar over here and you committed murder over here, they don't really care about the chocolate bar. They're going to go after you for murder. That's what it comes down to. Okay, let's look at the next file. Okay, this becomes more and more complex. If we look at this carefully over here, we have a multiplication there, division there. The first thing I would do is drop down the entire mess over here, just copy paste, convert that to a multiplication, and flip the fraction. In other words, convert division by a over b is equivalent to multiplication by b over a. That's all I'm doing over here. Now that we have nothing but multiplication, the idea is to factor all the quadratics. This is a quadratic, quadratic, quadratic. This can be factored, that can be factored, and of course that's linear, so you just leave it alone. This is an easy one to factor. It factors as x minus 2, x minus 3. That's difference of squares factoring. Factors as x minus 1, x plus 1. This is an easy trinomial factoring. That's what I call them. As I said, I'll be going through this in more detail in a subsequent video. So let's keep on moving here. This quadratic that easily factors is x plus 1, x minus 5. And the bottom is a difference of squares, which easily factors as x minus 2, x plus 2. The top is an easy trinomial factoring. It factors as x plus 1, x plus 2. And the bottom is linear, so all you do is drop it down as x minus 5. At this point, any factor in the numerator, the entire numerator, because you can think about this as an entire numerator, is able to cancel out with any factor, any identical factor appearing in the denominator. Okay, so cancel all means look for the factors that cancel. Let's look at x minus 2. Okay, let's see if we can find, oh, there's x minus 2 right there, so it cancels. There's x minus 3. Let's see if we can find it. No, we can't find it, so that remains. Let's look for x plus 1. Let's see if we can find it. Oh, there it is, so that cancels. Let's look for x minus 5. Let's look. There it is, so that cancels. Let's look for x plus 1. Oh, there it is, so that cancels. Oh, but that was already canceled, so that remains, because this guy canceled that guy, and it's gone. That remains. So we almost got burned there. Let's look for x plus 2. Let's scan. There's x plus 2 right there, and it was not previously canceled, so now it gets canceled out. Okay, so think about all the cancellations carefully. What remains in the numerator, you get x minus 3. That guy remains. And we get an x plus 1 that remains. And in the denominator, the x minus 1 remains. So this entire mess up here eventually reduces to this more manageable rational expression down here, and it's in factored form. Okay, so now we have to do a little bit of accounting. We have to remember all the cancellations that we did, and then we'll do 1/0 restriction at the end. Okay, so we're going to do the cancellations first and the 1/0 restriction at the end. And if you'll recall, we canceled out an x plus 2, so x cannot be equal to, or sorry, we canceled out an x minus 1, so x cannot be equal to 2. We also canceled out an x plus 1, so x cannot be equal to negative 1. We also canceled out an x minus 5, so x cannot be equal to 5. And we also canceled out an x plus 2, therefore x cannot be equal to negative 2. So this takes care of the 4 cancellation restrictions. Now we turn our attention to the reduced form at the end. Okay, we look at that denominator. We have to ensure that's not equal to 0. Otherwise, you'd be committing this crime. Okay, so to ensure that x minus 1 is not equal to 0, you make sure that x is not equal to 1. Notice this restriction does not appear on the left. So this is a true vertical asymptote restriction, and these are truly all whole restrictions. Okay, so again, to recap, the entire expression on top over here as it is equivalent to the reduced expression over here, coupled with the restrictions that were imposed at the end. You must impose these restrictions, otherwise somebody goes to jail or somebody dies, and that's something we don't want happening. And I think we're going to do an over and out for this video. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from MathLab Tutorials in Toronto.